Just imagine that scenario. Easier.
All right. Hi, morning. So just wanted to find out if people have any specific questions related to what we covered last time we met, which was the day before yesterday. I'm assuming you can hear me and you can see my screen, hopefully. No answer. Okay. At least Google Meet seems to suggest that you can hear me, so it doesn't matter if you don't answer. All right, so if there are no questions, then we proceed. Just a reminder that we have class tomorrow at 17 hours, right? So take note. And we also have class on Sunday at 17 hours as well. And just to put it out there that we'll probably spend the first quarter of the session tomorrow to look at quiz number 11, so just a short walkthrough. I don't know if we can call that revision or something. I'm concerned that a lot of people kind of like failed that. So we'll go through all the questions one at a time so that people understand exactly what was expected of them. So just to recap what we did the day before yesterday, we were looking at conversion of binary numbers into decimal and decimal or base 10 into binary or base 2, right? In terms of the conversion from decimal to binary, we realize that there are essentially two methods that we can take advantage of. So we can repeatedly divide a number represented in base 10 or in decimal by 2 by taking note or keeping track of the result and the remainder. And then once we converge, the heuristic we went through was such that as you repeatedly divide a number, you get to stop once the result is 0. Right? So we went through a series of examples. We also realized that there's yet another method that you can take advantage of, the so-called greatest powers of 2 method, right? Where you essentially get to subtract, you subtract from the decimal number that you're working with, that you wish to convert, the greatest power of 2 that is less or equal to that number, right? And I mentioned that it would be wise of you to experiment with all the different possible methods that are available out there so far as conversion of numbers is concerned, so that you identify a method that you are comfortable with, right? And you adopt that. This is not going away. It's coming back next year in 2020. I think 2021, or is it 2022 or something? It's going to come back at 4th year, right? So it's not like this is the end. Once we're done with 11, 10, that's the end. No, right? For some of you, once you get out there, once you leave the University of Zambia, you will find these things, right? Anyway, and then we also went through a process of converting from binary to decimal, and you do nothing more than just repeatedly multiply. Same heuristic as with conversion from hexadecimal to decimal, right? You repeatedly multiply the radix with the binary digits, right? So either 1 or 0. And we realize that actually when you're converting from binary to decimal, it's much easier, because as you're multiplying, it's either you multiply the evaluated power of 2 by 1 or by 0, right? And that number multiplied by 1 is still going to be that number, right? So essentially what you're doing is just adding up the result of evaluating the powers of 2 here that you're working with, right? Trivial stuff, really. Unless there are any questions, we are going to proceed and gain a sense of how exactly we get to do conversion from binary to hexadecimal. A reminder that we have mentioned from the outset that the bases that we are focusing our attention on are 3 of them, right? So base 2, base 10, and base 16, right? All right. At some stage, I don't know if it was the previous lecture, the lecture before that, I introduced this whole notion of the so-called nibble, right? So a grouping of 4 bits. It turns out that you tend to group binary numbers in groups of 4s because grouping them in that way gives you an opportunity to do a direct conversion from binary to hexadecimal in the event that you want to perhaps appropriately figure out what that number is all about, right? It's not always intuitive just by looking at this number to try and figure out what number this is, right? But what you can do is you can convert it to hexadecimal, and then you have a good enough idea of what that number is all about. So what we're saying is that you typically split these into nibbles, right? Or half a byte, like so, right? In which case this prefix by 0 anyway. So groups of 4s, if you're working with a binary number where you don't have an even distribution of 1s and 0s in that binary number, what you do is as you're grouping the bits from right to left, if there's a deficit on the group on the far left-hand side, you prepend it with 0s, right? So in this case, you notice that we had 3 0s remaining. So for us to get a nibble, we just prepend it with a 0, right? If you had 1 1 left, would have 2 0s prefixed or prepended, right? So the other reason why you might want to group bits like so is it makes it a lot easier for you to read the numbers, right? So imagine a situation where I'm just going to power up QtSpim here, right? Because I think it presents us with a perfect opportunity of how these things work. I'm simply going to change these values to binary. Observe, right? I have this number here, right? The status, I guess, in register number 5 has this value here. Simply telling you to say this is the number here makes it really difficult for you to decipher what this number is. It's confusing, actually. There's this continuous stream of 1s and 0s. What we are saying is you are better off grouping them into 4s, groups of 4s, nibbles, right? It's not that hard, right? And then if you have a deficit, you just do that. And then from here, actually, so readability is improved. Conversion, you soon discover from binary to hexadecimal is trivial. It's pretty much straightforward, right? Anyways, if this is making sense, but right. So this table is going to come up. So again, just to mention here that there's some significance associated with these groups of 4 bits, or the nibbles, or half byte. And the significance is that you can literally directly translate these 4 groupings here into the equivalent hexadecimal numbers, right? 0 through to F. And you notice this pattern that we have here, right? So 0 is represented by 001, right? This is trivial stuff, really. If you pay particular attention to do this, if you pay particular attention to this table, what you will notice, right, is that in fact what we're implicitly doing here is I guess we just call this hex, right? There's 16 or something. What we're implicitly doing is doubling back to decimal and then moving from decimal to binary, right? Yeah? Are you there, by the way? I don't know if they're there, but...
Yes, sir.
Yes, sir.
Yeah, okay, that's good. I don't know. So observe, right? So what we're saying is that this conversion from the nibbles we're talking about here. Imagine a situation where you have these 16 hexadecimal symbols, right? Because it turns out that the more symbols are associated with hexadecimal, right? When you're working with 2 symbols here, 10 symbols here, 16 symbols here. So we are saying that from 0 to 16, oh my goodness. What's happening here, right? I hate this sometimes, anyway, but it's like that. All right, so B, C, D, E, F, right? What we're saying is that for us to get the equivalent binary representation of these symbols, right? Since we're saying a grouping of 4 binary digits to represent either one of these symbols. There's a direct mapping. For us to get to the pattern, the bit pattern we'll be working with, all we would have to do is just do that, right? Convert this into binary, and then you have the binary representation of these decimal numbers here, right? So if we're using 4-bit representation, because we're saying for us to have a mapping of hexadecimal numbers to binary, right? All the 16 symbols, what we have to do is just represent the binary number using 4-bit representation, right? So whatever number we're deriving, it has to have 4 bits, right? So 0 base 10 into binary is 0, right? Which is 0, 0, 0, 0, right? 1 is nothing more than 0, oh God. 1 is nothing more than 0, 0, 0, 1, right? Remember, when you're working with binary numbers, we realize that you're working with, for you to evaluate those numbers, it's converting from binary to decimal here, you're working with powers of 2, right? 2 to power 0, 2 to power 1, 2 to power 2, 2 to power 3, 2 to power 4, right? And if this is ringing any bells here, right? 2 to power 3, 2 to power 4, 2 to power 5. So 2 to power 0, 2 to power 2 to power 1, 2 to power 2, 2 to power 3. For us to get 1, we know that we need to have a 1 here at the end, because 2 to power 0 is going to be 1, right? For us to get a 2, all we have to do is just make sure, for us to get a 2, this 2, we just have to make sure that we have 0, 0, 1, 0, right? For us to get a 3 is just a 2 plus 1, right? 2 plus 1, so meaning that we have 0, 0, 2 plus 1, right? We have the 3. For us to get a 4, it's just this bit here, right? So it's just going to be 0, 1, 0, 0, right? For us to get a 5, it's 4 plus 1, right? So the bit pattern we'll be interested in is this 4 and this 1 here. So for us to get a 5, we're saying that it's going to be 0, 1, 0, 1, right? Ooh, not 4, 0, 1, 0, 1, not 4, right? We get a 5. For us to get a 6, we're saying it's 4 plus 2, right? Which is 0, 1, 1, 0, right? For us to get a 7, all we're doing is adding 4 plus 2 plus 1. Yeah? 4 plus 2 is 6, 6 plus 1 is 7. So we're going to have 0, 1, 1, 1, right? For us to get an 8, it's just one lone bit here at the far left, right? 4-bit representation, remember? So it's 1, 0, 0, 0. Right? For us to get a 9, it's just 8 plus 1. So meaning that we need to add 1 and 1, right? For us to get a 10, it's nothing more than 8 plus 2. So meaning that we need to add 1, 0, 1, 0, 1, right? For us to get an 11, it's we're adding 10 plus 1, which is 8 plus 2 plus 1, right? So in here, for us to get 8 plus 2 plus 1, it's 8 plus 2 plus 1, right? And then for us to get a 12, it's 8 plus 4, yeah? So all we have to do here is just say, why? Let's just say, not say, that's 1, 1, 0, 0, right? For us to get a 13, it's 12 plus 1, so meaning that the bit representation we're working with is 1, 1, 0, 1, right? For us to get a 14, it's 12 plus 2, so meaning that the bit representation we're working with is 1, 1, 1, 0, right? For us to get a 15, obviously it's all 1, right? Because all we're doing is just adding up all these numbers here. 8 plus 4 plus 2 plus 1. 8 plus 4 is 12. 12 plus 2 is 14. 14 plus 1 is 15. So 3 1, 4 ones, right? So this is the thing here. This is the trick here when you're doing a conversion from binary to hexadecimal. Easiest way is to group. Excuse me. You're grouping. We're saying we are going to take advantage of the NIBO, right? So the 4-bit representation associated with the number you're wanting to convert from binary to hexadecimal. I hope this is making sense here. So if you look at these pretty trivial examples here, like 0, 1, 1, 0, you just have to either form a mental picture. It's pretty easy to form a mental picture of all these 16 hexadecimal symbols and their equivalent binary mappings that you're working with. It's not that hard. Once you do it over and over again, it's not really that hard. But if you're doing this in the exam, what you want to do is you write it down somewhere on a piece of paper like so, right? so that you know that this is what you're working with, right? This is a bit pattern you're working with. And then from here, you can easily derive the hexadecimal numbers, right? So we have a number like 010, 0110. We know that 0110 here, 0110. It's a 6, but it appears somewhere here. Because of spacing constraint, we omitted some numbers here between 3 and 9, right? So we don't have 4, 5, 6, but it's a 6, right? And we can prove it by coming here. 6 is 0110. Are you following here? Are you there?
Yes, sir.
Yeah, okay. All right. That took you long enough. That's fine anyway. So you notice what we're saying here is if you're converting a binary number that only has, let's say, 4 placeholders or less, it's a lot easier for you to convert it to the equivalent hexadecimal number, right? So for instance, 1100, it's a C, right? Here's a question for us. What is 11? No, not 11. What is 11 base? What is 11? What is 11 base 2 into hexadecimal? If you're following. Because what we're saying is it's a lot easier for us to derive hexadecimal symbols when we're working with binary numbers that only have 4 placeholders or less. This is 4 placeholders or less. This is 2 placeholders, right? 11, there's 2. How would we convert this to hexadecimal using our mapping here? 11 base 2. What is 11 base 2?
It's 83, sir. You said
Sorry? What is 11 base 2 in hexadecimal?
3.
Yes, exactly. It's here, right? So the trick here is what we're saying is if you have a binary number, excellent. If you have a binary number that has placeholders that are less than 4, you prepend the number with zeros, right? So essentially, what we're saying is 11 base 2 is the same as us saying what is 0011 base 2. This is what we're saying here, right? One and the same. One and the same. Wow, I don't know what this is all about, but anyway, don't know what is it. So it's not that hard to convert these smaller numbers, right? But of course, when you start converting these significantly larger binary numbers, so numbers that are composed of more than 4 bits, for instance. If you could mute your microphone, that would be good. It requires a little bit of not a lot of imagination per se, but you have to remember this notion or idea that you should segment your binary number into nibbles or into groups of 4s.
So
Yes.
I didn't really understand on the conversion process. Can you just go back to that chart you made?
Yes.
Yes. I didn't really understand how the conversion process was moving as we are going down, as the numbers are accumulating on the decimals, how the binary numbers were increasing from the 01 coming to 11, then 001. I didn't really understand how you're doing that.
Oh, okay. Well, it's so what we were doing here, what I was doing here is I was taking advantage of, I was doing decimal to binary conversion. For me to get the hexadecimal, the equivalent base 2 of these hexadecimal symbols, I need to double back to decimal. So what I did actually is, first step is I converted these symbols into decimal, and then decimal to binary. This is what human beings find easier to work with, right? You first of all go the other way, decimal and then decimal to binary. So observe what we're saying here is that it's like what we're converting here. If you look at these numbers here, right? what we are doing here is we are saying what is 0 base 10 into base 2. So what I was, so imagine a situation where we are converting these, right? Maybe this will make, tell me if this is making sense or not. Maybe not, I don't know, but maybe it will, maybe not. This is sad, eh? Let's see if we can do that. Beautiful. So here's the thing, right? We're saying what is 0 base 2? We've already done decimal to binary conversion, right? Yes?
Yes, sir. Yes, sir.
Yeah. So we're saying what is 0 base 10 to base 2? And if what I'm doing essentially is I'm doing what? For me to get the equivalent binary number of these numbers, I'm just doing repeated division by 2. Right?
Yes,
2
yes, sir.
divided 0 divided by 2 is 0, remainder 0, right? Which is 0. But we are saying that when we are because we're doing this conversion so that we understand exactly how to convert from hexadecimal to binary. One of the key things to keep in mind when you're doing conversion from hexadecimal to binary or binary to hexadecimal is you need to represent your binary numbers into groups of 4s. So even though the number 0 base 10 is 0 base 2, you want this to be represented using 4-bit representation, which is 0, 0, 0, 0, right? Boom. What is 1 base 10 into base 2? All we do is repeatedly divide by 2, right? That same method here. What is, I guess this is the quotient or result or something, this is a remainder. What is 1 divided by 2? The answer is 0, remainder 1. Okay? So we see that 1 base 10 is 1 base 2. But we need to represent this using 4-bit representation. And so we say we prefix or we prepend the 1 with 3 zeros. What is 2 base 10 to base 2? All we're doing here is repeatedly dividing 2 by 2. 2 into 2 is 1, remainder 0. 2 into 1 is 0, remainder 1. So the answer here is 1, 0. But what we, 1, 0, right? It's like the scores. But what we're saying is using 4-bit representation, we prefix this with 2 zeros so that we have a nibble, or we represent the answer with using 4-bit representation. I'm going to go everything here, through everything, but let's double back, or let's move forward to 10, for instance. It's the same thing, right? We repeatedly divide 10 by 2. What is 2 divided by 10? It's 5, remainder 0. 5 divided by 2 is 2, remainder 1. 2 into 2 is 1, remainder 0. 2 into 1 is 0, remainder 1. We converge. The answer here is 1, 0, 1, 0, right? 4-bit representation. This is 10. And so what I was doing here, I was doing this because the numbers are pretty easy to work with, right? Think about this for a second. If you're working with, I hope this is making sense, Clarence, right? Does this help?
Yes, sir. It's making sense.
Yeah.
Thank you.
So I want to draw attention to, because when I was doing this conversion, right, and probably this is where confusion came in. I've already formed a mental picture in my head insofar as how these numbers work, right? It's very easy to work with these numbers. All I'm doing is I'm playing around with the placeholders associated with the powers of 2. 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3. I evaluate them. 2 to the power 0 is 1, 2 to the power 1 is 2, 2 to the power 2 is 4, 2 to the power 3 is 8. And using these numbers, right, using different combination of these numbers, I'll be able to derive these different answers here. For me to get 15, I just need to add 8 plus 4 plus 2 plus 1. I'll get 15. You understand? 8 plus 4 is 12. 12 plus 2 is 14. 14 plus 1 is 15. Meaning that for me to get 15, all of these placeholders must be 1s. 1, 1, 1, 1. This is making sense. Now look at this. If I want to get 7, for me to get 7, I just have to add 6 and 1, right? For me to get 6 and 1 using this small little table I have here, I need to have a 1 against here, a 1 against here, a 1 against here. Which is why 7 here is 0, 1, 1, 1, 1. So it's I don't know if this is making sense or if it's confusing people, but if this is not making sense right now, what you want to do is you want to you just want to draw your table, right? Yes, I know it's boring, right? Why are we drawing tables? But you draw your table on a plain piece of paper and you practice. When you practice these things over and over again, it becomes muscle memory, and all these things will be just trivial stuff. By the way, right? There's a method to the madness. Very, very soon we start looking at the math, right? Arithmetic, actually, addition and subtraction, division and multiplication. So what we're doing is doing multiplication and addition of these ones and zeros. This is where we're trying to get at here, by the way. So just wanted to put it out there that we are doing some of these things because the time is coming very, very soon, right? I think it's hopefully not today, maybe tomorrow or something. All right. So this is, I hope this makes sense. It's very easy for you to do a conversion with, you don't have to draw this table actually. You just look at a number. When do you get 8? You get 8 by adding 6 and 2. Sorry, you get 8 by just adding 8, right? You have an 8. You have a power of 2 that will give you 8. How do you get 11? You add 10 and 1. How do you get 10? 2 to the power 3, which is 8. 2 to the power 1, which is 2, and 1. 8 plus 2 is 10, plus 1 gives you 11, right? This is here. And then you know that you'd have 1, 1, 1, which is 1, 0, 1, 1. I don't know. Anyway, I hope this makes sense. I don't know if it's confusing people, but if it's confusing you, just draw this table, all the 16 symbols somewhere, and then convert them from decimal to binary. But your answer should be represented using 4-bit representation. Yeah, sure. Hi.
So would it be wrong if you are asked to convert decimal into binary, then we present it in 4-bit representation?
If you what?
You are asked to convert a number from decimal to binary, then when given your answer, you present it in 4-bit representation. Is it wrong?
Not quite. I mean, it depends on the magnitude of the number, right? So think about this for a second. This 4-bit representation, and we'll talk about overflow very, very soon, by the way. It's an interesting concept because it's a serious thing in computing, right? So you have to be very careful about this, right? Because 4-bit representation only works for numbers up to 16, I believe, right? Observe. How do we get to 17? What is 17? 17 has to be 2 to the power 4 plus 1. So for you to get 17, if somebody tells you convert 17, here's the thing, right? Somebody comes up to you and tells you convert 17 into binary. Repeatedly divide by 2, right? Quotient and result, I guess, I don't know. 2 into 17 is 16, remainder 1, right? Sorry, 8. Remainder 1. 2 into this is 4, remainder 0. 2 into 4 is 2, remainder 0. 2 into this is 1, remainder 0, right? Then 2 into 1 is 0, remainder 1, yeah? The answer is, observe, right? The answer, you can't represent this, there will be an overflow if you try and represent this number using 4-bit representation. Why? Because your answer is 1, 1, 2, 3, 1. Now, if you represent it using 4-bit representation, you have to exclude the 1, which actually gives you 1, right? This is no longer 17, this is 1. So it depends on the context. Usually, if it's a question, if it's a problem set that you're working towards, it will be explicitly stated. Represent your answer using 8-bit representation or 4-bit representation. Usually, it's 8-bit representation. Why? Because the smallest unit of data we've discovered is a byte. A byte is 8 bits. It's almost always the case that you represent the answer using 8-bit representation or something. I mean, certain weird instances, like if it's a more practical question, like for instance, integer representation, because integers are 32-bit in size, you perhaps would be told represent your answer using 32-bit representation. These are 32 bits, by the way, in your registers, yeah? I mean, it's 64-bit process, or probably have like a different number of registers. So it depends on the problem you're solving. Usually it will be explicitly stated. I hope that answers your question. No, I don't know. Somebody's not answering. Does that answer your question?
Yes, sir. Thank you.
I thought so. All right, great questions. These are questions you should be asking, I suppose. I don't know if I was asking these questions when I was student myself, but anyways. So what we're saying is like converting a relatively large binary number is trivial, right? If you latch on to this idea of representing the binary number into groups of 4s using nibbles, right? It's very easy because all you do is you come up with a little translation of the hexadecimal symbols that are represented by these numbers here. Do you understand? This is what we're saying here. All you do is the heuristic, probably one of the simplest heuristics when it comes to conversion from different number systems, right? So what we're saying is you first of all just group your binary digits into groups of 4s, right? Nibbles, and then you convert the groups into decimal equivalents, and then the decimal equivalents should be converted to hexadecimal. So using that table of yours, if you look at this number, it's excellent. Actually, we did this, right? You look at this number, and you can literally see that this is 1 plus 2 plus 4, right? This is 7, is it? Right? Is it 7? Oh, no. Yay! 2 to the power 1, 2 to the power 2, 2 to the power 3. 2 to, oh, sorry, 2 to the power 0, 2 to the power 1, 2 to the power 3. 0, 1, 3. Sorry, 0, 1, 2. So it's 4 plus 2 plus 1. 4 plus 2 is 6, 6 plus 1 is 7. 1, 1, 1 is probably the simplest here. We know that this is 15. This is going to be 15. This is going to be 15. And we'll go through examples, but I thought I'd latch on to this thing here that I already had here. It's going to be 1. This is going to be 0, 0, 1, 2. So this is going to be 0, 1, 2. This is going to be 4. Right? And then what we do afterwards is, this is decimal representations. What we do afterwards is we convert the decimals to hexadecimal. It's pretty easy for these symbols that are less than 15, right? 0 through 15, the decimal symbol 0 through 15, because we know that 7 is 7, 15 is F, 15 is F, 15 is F, 15 is F, 7 is 7, and 1, and then 4. So this number here, this long, this 2-bit represented binary number here is nothing more than 7, 1, 2, 3, 4, 7, 1, 4. And really, if we were to go back to QT Spring where we got this number from, and I just configure my simulator so that it shows me the number, this is the number we're converting here. It's one and the same, right? So process of the heuristic is quite simple. You first of all you group the digits into groups of 4s, right? The binary number into groups of 4s, and then you convert the nibbles or the groups of 4s into decimal, and then the decimal number should be converted to hexadecimal, and then you'd have done your conversion. Quite simple, because all you're doing is you're working with these 15 symbols here, right? So here's the thing. Here's a simple example, right? We're going to start with this really strange number here, 1, 1, 1, 1, 1, 1, 1, 1, 0, 0, 0, 1, 0, base 2. So we convert this to base 16 or to hexadecimal. What's the first step? We must first of all group these numbers into groups of 4s. This is going to be our first step. We cluster these into groups of 4s. Remember, as you are clustering, as you are grouping them into 4s, and you come across a situation like this situation we're in right now, where you have a lone group, the last group has placeholders or bits that are less than 4. You prefix or you prepend a 0, like so that it's a group of 4. It's going to be a lot easier for you to work with, right? So it's a process. You group them into groups of 4s, like so. The next step here is I'm prefixing, because it has to be groups of 4s, right? It has to be 4. It has to be nibbles. I prefix or I prepend this last group here because it has 3 digits with a 0. And then afterwards, I'll convert these numbers here, these groups of 4s, into the equivalent decimal numbers. And then I convert the decimal numbers into hexadecimal. I know that 2 is 2, 7 is 7. What is 14? E. Okay. Is this, I don't know if this is making sense. Is this making sense? And then your answer will be 7E2 base 16. Again, I just want to point out there to you guys that very, very soon you will see very weird things like this 7, I think I mentioned this already. This 7E2 could just as well be represented like so. These are different ways of representing hexadecimal numbers. And this thing, by the way, right? This number representation that you have, 0x7E2, you will find this in 2010. When you're programming, it's quite common for you to represent your numbers in base 16, like so, using this notation. Very useful notation. Why are we doing this, you might ask, right? Well, it turns out that your program is much more elegant that way. Yeah? If you represent the numbers in hexadecimal, it's much easier that way. But I guess, I don't know if that makes sense. But so simple process, right? Very trivial process. You group into 4s, convert the groups of 4s into the equivalent decimals, convert the decimals into hexadecimal, right? And then you get your answer. Again, you notice that what we're doing here heavily uses that table introduced a while back, right? And where is that? This thing here, very important. Especially if you're doing this for the first time. But once you do this over and over again, you realize that it's going to be relatively easy to do your conversion because it becomes muscle memory. And in fact, I mean, think about this for a second. You know that A is 10, B is 11, C is 12, and then F is 15. It can't be that hard for you to convert 15 into binary, right? No, it's not that hard. Because all you're doing is, if you just think about the conversion from the point of view where you are working with powers of 2, where you start with 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4, 2 to the power 5, 2 to the power 6. Life will be so much easier for you, right? But I mean, if this is not intuitive, you can always do it physically, right? You write the powers of 2, 0, 1, 2, 3, 4, 5, that's that, right? And then you convert, oh, what is 2 to the power 0? 2 to the power 0 is 1. 2 to the power, what is 2 to the power 1? No, spreadsheet to do this for us anyway. I don't know. Is this making sense?
Yes, sir.
Yeah. So here's the thing, right? Just a simpler conversion, right? And I'm using different scenarios here where, because when you're doing this for the first time, this idea of grouping the binary number into groups of 4s can be a bit confusing, right? Just remember you must prepend or prefix lone binary digits that have placeholders that are less than 4. And this is a classic, another example here. So we cluster this into groups of 4s from right to left, yeah? So you notice that we have 0, 0, 1, 0, and a 1. What do? We prepend 3 zeros to the lone 1 there, right? So we have this. And then we convert these numbers into the equivalent decimal numbers. 2, 1, right? Then we have 1, 2. No need for us to convert these into the equivalent hexadecimal symbols, but if you're doing this for the first time, the next step is convert 1 into its equivalent hexadecimal, convert 2 into its equivalent hexadecimal, and this is just 1, it's going to be 2, right? And then afterwards, your answer, this is your answer, 1, 2, base 16, right? Or some people would say it's 12 base 16. I don't think so. It's not 12 base 16 here, right? 12 only exists in decimal or base 10. Let that sink in. This is not 100,010. No, this is 10010 base 2. All right. I don't know if this is sinking in. Right?
Sir.
Yes, sir.
Can you kind of go over this example? I lost it. Where after you just grouped binary digits into 4. I just.
So.
Do you mind?
No, I don't mind. I mean, so that's fine. So you're saying with 10010, right? This is what we're converting, 10010. Observe, what we're saying is, the first step, step 1, group digits into 4s, right? So we'll have, from right to left, we have this number grouped into 4s. 1, 2, 3, 4. Right? Step 2, make sure that when you group them into 4s, well, this is still grouped into 4s. Because this has a single digit, we need to prefix this with zeros until we get a group of 4. So what we have here is 0, 0, 0. Yeah. Step 2, convert groups into decimal. So we're saying this needs to be converted into decimal. And converting this into decimal is easy because we went through the process, right? How do we convert these groups of 4s into decimal? Do you remember what we do? Repeated multiplication. So effectively what we're doing is we get 0, 0. We'll start with the rightmost, right? 0, 0, 1, 0. What is 0, 0, 1, 0? What is 0, 0, 0, 0, 1, 0 into 0, 0, 1, 0 base 2 into decimal? It's simple. We repeatedly multiply 0, 0, 1, 0. We get the powers of 2, right? 2 to power 0, 2 to power 1, 2 to power 2, 2 to power 3. We evaluate the powers of 2. 2 to power 0 is equal to 1. 2 to power 1 is equal to 2. 2 to power 2 is equal to 4. 2 to power 3 is equal to 8. What's the next step? We multiply these things here by the evaluated powers of 2. So it's 0 times 8 is 0. 0 times 4 is 0. What the hell is this? 2 to power 1. 1 times 2 is 2. 0 times 1 is 0. What's the final step? We add 0 plus 0 plus 2 plus 0 is 2. So what we are saying is 0, 0, 1, 0 is 2. Right? Convert this into decimal. We convert 0, 0, 0, 1 into its equivalent. And I know you're thinking, nah, why are you doing all of this? You're too slow now. But just for the benefit of those that might be a bit confused, this is why we're doing this. In case it might be confusing, because we're jumping steps now, assuming that you understand conversion from binary to decimal, because we did this already. So we convert 0, 0, 0, 0, 0, 1 to base 10. What is this? We do the same thing, 0, 0, 0, 1. We get the powers of 2. Evaluate these powers of 2. This is going to be the same answer. And then we start multiplying. 0 times 8 is 0. 0 times 4 is 0. 0 times 2 is 0. 1 times 1 is 1. So the answer here is 1. This is 1. And then we're done, right? So it's 1, 2. The next step is step 3. Convert decimal numbers into hexadecimal symbols. Right? And it's simple here. 1 in hexadecimal, this is decimal, right? These are decimal now. So these symbols, you convert them to hexadecimal. What is 1 base 10 to base 16? It's 1. What is 2 base 10 to base 16? It's 2. So the answer is actually 1, 2 base 16, yeah? Does this help?
Yes, sir. Very much, actually.
All right. Okay. So what about then? How do we do the opposite, right? So how do we convert from hexadecimal into binary? Well, it's easy, right? Because we are saying that a nibble, right, or groups of 4 bits will represent a hexadecimal symbol. Then what we can do when we are converting hexadecimal numbers is we can use those symbols to convert them. We use the symbols to convert them into the equivalent. There's 2. Do you understand this? So we are doing the reverse actually. So symbols into decimal and decimal into binary. This is what we're doing. A very trivial process. Observe what we're saying. What we're saying is if we latch on to our example where we have QT stream, right? We want to convert this number here, hexadecimal number here. This hexadecimal number here, 7FF71C, yeah? What we're saying is, because when you're converting from binary to hexadecimal, we are saying enable is going to give us the representation we want, then doing the opposite is true. We separate these into the equivalent symbols, and then we convert the symbols into the equivalent base 10. Converting them into base 10 is trivial. 7 is 7, F is 15, F is 15, another F is 15, another F is 15. 7 is 7, 1 is 1, C is 12, right? And then you convert these lone decimal digits here into base 2. Do you understand this? Now there's something really interesting happening here. If you have access to this table here, it becomes a lot easier, right? Because all you do is just do a lookup here. Oh, what is 7? It's 0, 1, 1, 1. But if you don't have it, I mean, deriving 7 into base 2 here it's a trivial thing, right? Because you're working with, you see, when you're working on 2, I guess I could use a tab. Yeah, tab is good. Because you're, 2 tabs, I suppose, I don't know. Because you're working with, I don't know, maybe 2 tabs are probably overkill or something. Nah, it's overkill. Because you're working with, I overdid it, I suppose, yeah. Because you're working with just 4 digits, it's very easy for you to translate this into the equivalent base 2. How do you get to 7? You get to 7, just assume you just have 4 placeholders here, right? 4. How do you get to 7? You get to 7 by adding 4, 2, and 1. You understand this? How do you get to 15? Guys, what I'm going to do is I will just, I think it's going to be a lot easier if I put it in a spreadsheet. Spreadsheets are nice, like they're teaching us in 1020, right? So 7, 7, F, 1, 2, 3, 4, right? And then 7, 1C, 7, 1C. Here's the thing, observe what's happening here. What we're saying is that converting this number here into base 2 is very easy because you go through a step where you convert to decimal, and then after you convert to decimal, you convert to binary. Converting 7 to decimal, if you want to use the method we used, by all means do that. What you do when you're converting a decimal number to hexadecimal to decimal, the first thing, because we're working with just 16 symbols here, is you convert, you take note of the equivalent decimal symbols that represent these numbers. We know 7 is 7, F is 15, F is 15, F is 15, F is 15, 7 is 7, 1 is 1, C is 12, ABC, 10, 11, 12. Once you do this, as a next step, we are saying we need to convert these now, these decimal symbols, into binary. How do we convert these into binary? Repeated division. So we repeatedly divide 7 by 2. If you don't want to form a mental picture, repeatedly divide, right? Follow the rules. If you're doing something for the first time, I guess you just follow the rules. So 7, repeatedly divide by 2. 2 into 7, the answer is 3. Remainder 1. Yeah. Wow. 2 into 3, the answer is 1. Remainder 1, right? 2 into 1, the answer is 0. Remainder 1. What is the answer? 1, 1, 1. So in here, we're saying 7 is 1, 1, 1. But remember, we are saying it's a lot easier for you to convert by representing these into bits of 4s, groups of 4s. So in effect, this is 0, 1, 1, 1. Understand this? 0, 1, 1, 1. So this is 7. What is 15? Repeatedly divide 15 by 2, right? 2 into 15, the answer is 7. Remainder 1. 2 into 7, the answer is 3. Remainder 1. 2 into 3, the answer is 1. Remainder 1. 2 into 1, Ms. Banda said it can't or something. 2 into 1, the answer is 0. We converge. Remainder 1. The answer is this. We already have 4 bits here, so the answer is just 4 bits, right? It's already 4-bit representation. 1, 2, 3, 4. The other 15, I guess it's already consistency sake here. The data type is different. So the other 15 is just 1, 1, 1, 1, 1, 1, 1, 1, 1. And this is a 7, so it's just going to be this. Is this making sense? What of 1, right? Repeatedly divide 1. What is 1? 1 base 10 into binary. Repeatedly divide 1 by 2. 2 into 1, 0. Remainder 1. So the answer is 1 here, but using 4-bit representation, it's going to, we need to prefix 0, 0. It has to be 0, 0, 0, 1. What is 12? Repeatedly divide 12 by 2. Yeah. 2 into 12, it's 6, remainder 0. 2 into 6, it's 3, remainder 0. 2 into 3, it's 1, remainder 1. 2 into 1, Ms. Banda said it, it's 0, remainder 1, right? So your answer already 4-bit representation here, it's 1, 1, 0, 0. 1, 1, 0, 0. Now, here's the thing about forming a mental picture. You keep mentioning about forming a mental picture. You just have to think here. Powers of 2, 4, or 8, 4, 2, 1, 0. Which combination will give me 12? It's 8 and 4. 8 and 4. Anyway, and then your answer is going to be this thing here, right? So we're saying 7F, 7, 1C. The answer is here.
Sir.
Yes, sir.
When we were dividing 1, did we start from the bottom up when putting it?
Yes, because 1 is 1, right? Here. 2 into 1 divided by 2, the answer is 0. Remainder 1. Now, if you only have 1, does it matter whether you start bottom? We did actually bottom to top, but it's just one symbol we're working with, right? So
so it doesn't matter whether left to right. It's just supposed. It's going to be. You can put it anywhere, whether the front, the first, or the last.
No, I mean it works best if you follow the rules. The rules say it's bottom, top, right? So if you're saying when you repeatedly divide 1 by 2, the answer is 1. Bottom to top will still give you 1, right? So it's 1, but all we have to do is prefix this with 3 zeros, and then we have 00001.
Oh yeah, it makes sense now. It makes sense.
Yeah, I thought you did as well. So and then you come up with this answer, and then your answer is going. Now here's the thing, right? The interesting thing about depending on the type of application that you're working with, sometimes it could be the case that your application will remove trailing zeros. Yeah. So observe something here. If I count these bits, right? Ooh, where are we? Is here. If I count these bits, yeah, these bits will be. I don't know if you can see my count here, but if I count these characters here, I'm just going to view this and say show word count or something. You notice that where is that thing? Oh wow, it's not showing. That's strange. Oh, there we go. So 32 characters. You notice there are 32 characters. Now, sometimes, depending on the type of application that you're using, this trailing zero will be removed. Observe in QT-SPIM, right? This is the number we're converting register 6 or A2. If I change this to binary, look at this. If I copy this and paste it here and count the number of characters here, this will be 31 characters, not 32, right? You see this, 31 characters. Why? Because it's pointless for you to include a trailing zero here, but there's no harm in including it anyway. Okay, so tomorrow we're just going to walk through these examples that are in the slides, and just to reinforce this before we transition to, we'll look at some more examples where we get to look at large numbers before we transition to addition of I mean, the basic arithmetic associated with binary numbers. So look at addition, subtraction, multiplication, division. I don't know, I keep talking to some of my friends and asking them, do you think that we should advocate for a change in the curriculum where counting should now be done in binary, right? Computers are everywhere. I'll see you when you see me, which is tomorrow at 17 hours, I believe. Stay safe and goodbye. Thank you.
Bye, sir.
Yeah.
Someone kindly stop the